Okay. Morning, everyone. Everyone needs to say English. First English. You prefer English. Okay. So we are very happy to host Noam with us today. He's a postdoc in the Princeton Language and Intelligence Institute, it's PLI, working with Santiago Roa, mainly, I guess, right? He did his PhD with us, with Noam Cohen. And he's doing all stuff related to AI, right? Okay. Well, no, man, very, nice to try today.
Okay. Thank you for having me. It's great being back. So it's no secret that the field of deep learning or AI, depending on who you ask these days how the field is called, is going through a paradigm shift. The early measure of success around the 2010s was primarily driven by task-specific AI. For any task that you had a good amount of data for, training a neural network over it often led to breakthrough results. And this is something that happened across numerous different application domains. In the past 5 years or so, however, there's been a major shift in focus from these task-specific models to general-purpose models such as ChatGPT. These models, they leverage the flexibility of natural language as an interface to perform a wide array of tasks. This can be mundane ones. They can give you recommendations for your next trip abroad, to solving code problems, math problems. The list of potential applications here just goes on and on. And today we're at a time point where these models are being widely adopted in society because they're so useful. Yet we can no longer empirically verify all the different design choices that we make. At the largest scales, we can't just run multiple different configurations and choose the best one. This is becoming too expensive. And these two factors, combined with the fact that our theoretical understanding of these models is also very limited, they give rise to a need for having more principled guidelines as we train and deploy general purpose models. If we want to ensure that this is done efficiently, that we don't want to waste too much resources, reliably, and of course, to keep increasing their performance. And my research aims to address these challenges by focusing on the fundamentals and to develop theories that explain how what we do, this is the algorithmic choices that we make, affect what we get, this is the capabilities of the model. And through this better understanding, to impact practice. My typical approach involves a tight combination between mathematical theory and analysis and experimentation. This includes controlled settings, but also importantly, real-world settings as much as possible. If you put online the scale of experiments that one can run, and on one hand, you have small-scale results where the models maybe have a few thousands or millions of parameters, and the datasets are quite simple. On the other end, you have industry scale. Okay, nobody knows, but it is speculated that the models being run today have trillions of parameters. So we obviously can't operate at industry scale in academia, but the type of experiments that I aim for in my research, and also that I'm going to show today, is on what you can call an academic large scale. Okay, the largest scale that an academic budget permits these days. The models can have billions of parameters and are quite decent for some purposes at least, and the data sets are also relatively realistic.
You seem to be excluding the possibility that observation would lead to insight, as opposed to just analysis or experimentation.
No, so actually I'm not excluding it. So in my point of view, mathematical theory and experimentation are both tools for getting better understanding.
So what I meant is when industry runs these models at industry scales, there is a huge amount of data about the prompts or queries and answers, and possibly it might be possible to do observational research without controlling anything.
This is also true, yeah, perfectly valid. I'm not saying that this is not that. So again, also the type of observational experiments that you can run are often not at the scale that you can do in industry. Maybe that, obviously not excluding this. And perhaps, in my view, just to say that this combination of theory also with experimentation is important for making progress, given the complexity of current models and settings. Right. So in terms of my research timeline, I did my PhD here, where I focused on task-specific models. In particular, my research during my PhD mostly addressed two central questions about the theory of neural networks. First relates to generalization. Okay, how are neural networks often able to generalize well, even when they have far more vulnerable parameters than training examples? Okay, we know that they can wholly overfit in these cases, but they don't. And the conventional wisdom is that the training algorithms that we use, they induce some form of an implicit bias that guides us towards predictors that are simple. And the question is, in what sense are they simple and how that leads to generalization? The second related question is, okay, neural networks work great, but not on all types of data. And for different data types, different architectures can work better. Can you understand what makes a certain data distribution compatible with a given architecture? And the tools that I used were adopted from the field of tensor analysis, and dynamical system theory. The details of this line of work is more a story for another talk. But just to give the main highlight, that we showed that notions of rank, you can think of this as generalizations of matrix rank to arbitrary functions, they can be useful for explaining the performance of neural networks, at least in some settings. Okay, we established that for several different architectures, there is a notion of rank that is being implicitly minimized during training, meaning you learn a predictor that has low rank. And we also use these same notions of rank to characterize what makes given data distribution compatible with a given architecture. And our theory also had practical impact. We developed based on regularization schemes, data preprocessing algorithms. I'm still very much excited about this line of work, but what I will focus on today is research I've been doing since an internship at Apple towards the end of my PhD, and as a postdoc now at Princeton. And this is work on general purpose AI, specifically on characterizing and overcoming pitfalls that can occur when you try to align these models with human friends. Okay, to unwrap what I mean by general purpose models, I would like to start by highlighting three aspects which I feel are fundamental ingredients of these types of models. Because the first aspect is world knowledge. This is what allows us to interact with them about general concepts of the world, typically through natural language. Okay, the way that this is currently implemented is based on language models, which get their knowledge by training them on large-scale internet data, train them to predict the next word. And to be clear here, a language model for our purposes is nothing more than a neural network that gives us a distribution over sequences of tokens. Okay, we're going to denote by pi theta, our language model. Theta is the parameters that we learn. We can give it a prompt X. This is, you can think of a question that people ask ChatGPT, and it gives us a distribution over possible outputs Y. Now, these tokens, they can be parts of text, they can be image patches, audio, video, any other modality. There's nothing specific in the results that I'm going to show next, but just for simplicity and to be consistent with current terminology, throughout the talk, I'm going to use the term language model to refer to the current implementation of general purpose AI. Okay. The second aspect is alignment. And this broadly refers to how do we ensure that these models do what we expect them to do. And this can amount to complying with human preferences, producing safe and helpful outputs, following the instructions that we give them, maybe even having certain skills like solving math problems. Alignment can mean different things to different people. Here I'm being very high level. And in a few slides, I'll be more formal, precise about the type of alignment which we consider, which is the alignment that people do now in practice. Okay. And lastly, there is inference. As opposed to, say, image classifiers, which give you just a single label at the end. There's not much flexibility to it. General purpose models produce highly complex outputs. Okay, this can include intermediate reasoning tokens. They can use external tools like search. And the outputs are also highly structured and often contain natural language. And this creates the challenge of how should we best generate outputs and scale the compute that we have at inference to get better results. Okay, the language model, it gives us a distribution over outputs. So the most straightforward thing to do, we can just sample one. But maybe you can do better by sampling multiple outputs, trying to choose the best one. Or you can be more fancy and have multiple models iterating over the output until they give you the final answer. Understanding general purpose models, in my view, will require understanding these three aspects, among others. And in today's talk, we're going to focus on one of these aspects, on alignment, where the guiding question behind the research that I'm going to present is, what is necessary for efficient and reliable alignment? Okay, so with this high-level introduction in place, we can now start making things more concrete, right? The way that language models are currently aligned is typically based on preference data. This means that you start from a data set where each example is a triple. You have a prompt X, and it is associated with usually two candidate outputs. You can get them by sampling them from your current model. You can source them from the internet. Either way, the label you need here is which output is preferred. Okay, here Y plus is preferred over Y minus. The underlying assumption, the existing paradigm, is that there exists some unknown ground truth reward, RG here, which captures at least some aspects of human preference. And the fact that we see that Y plus is preferred over Y minus, that simply translates to Y plus has a higher ground truth reward. Okay?
Assuming higher ground truth reward, this is unlike most the theory. Usually, there is some solution that depends on those two values.
Great, yeah. So this is a bit simplified. Often you assume some kind of noise or distribution. So assume that you have a reward, and then the reward gives you a distribution of how likely is Y plus going to be preferred over Y minus. This won't really come into play into the analysis because we're not going to consider this part of the pipeline, but it's true. So you can assume different connections between the reward and the preference data, whether it's deterministic or some distribution like Bradley Terry model, but this won't matter for this topic. So both are perfectly fine. And once you have this formalization, you can consider the goal of alignment as you want to maximize this ground truth. You want the language model to produce outputs that achieve a high reward. And this is the formal goal of alignment under this paradigm. Of course, it's debatable whether this is a good goal. It's a good question. Okay, if there are certainly aspects that it doesn't capture, but this is the type of alignment we currently do, and this is what we're going to focus on now. And in the end, we're also going to discuss perhaps how we go beyond that. Right? So the challenge here is that we want to maximize this ground truth reward, but we don't have direct access to it. Okay, we can only access it through preference data. And there's two approaches for solving this today. The first one is based on reinforcement learning, and the second is a more direct approach of aligning the model from the preference data. And we're going to cover both of them in this talk, where the recurring theme behind the results that I'm going to show is that their limited understanding can lead to undesirable outcomes. This is the plan for the remainder of the talk. I'm going to first focus on the reinforcement learning approach for alignment. This is also the main technical component. It's based on 3 papers, the first done at Apple and the second two at Princeton. We will then more briefly discuss the direct preference learning approach, and then I'll conclude with future directions. Okay, so aligning language models using reinforcement learning. This is known as RLHF, reinforcement learning from human feedback. It's a 2-step process. First, we don't have the ground truth reward, so let's train a proxy reward model. This is a neural network that we train over the preference data by minimizing some loss that encourages it to give a high reward to Y plus compared to Y minus. Okay? And once we have this proxy reward, we can align our language model by maximizing it over some set of prompts using your favorite policy gradient. So there are several policy gradient methods from. They all pretty much amount to the following objective using gradient-based methods. Okay, so we're maximizing with respect to our language model, pi theta. In this context, it is also known as the policy. If I'm saying policy, I just mean language model. I'm going to use these two terms interchangeably, policy, language model. And the objective is, okay, you have an average over your training set in 2 terms. The first is we want to increase the proxy reward. Okay, hopefully, if the reward model is any good, this should also increase the ground truth reward that we care about. The second term is a KL divergence regularization from the initial policy, where the idea is to restrict how much we deviate from it so that we don't lose capabilities that the model had before we started. Okay, so this is our RLHF in a nutshell, these 2 steps. And its success heavily depends on the quality of the reward model, right? In the end, it provides the signal of learning. But it is actually not clear how we should evaluate this quality. Okay, the way that people currently evaluate reward models is through their accuracy in ranking pairs of outputs. If you take a data set of these preference examples, accuracy measures the fraction of these that the reward model ranks correctly, meaning that gives a higher reward to Y plus compared to Y minus. In existing benchmarks, they give you a list of which reward model is more accurate over their fixed data set. Now, actually, the natural measure to look at, okay, intuitively, it quantifies how likely are we to increase the ground truth reward if we maximize our proxy. If the reward model is very accurate, then outputs it considers to be good are probably also good under the ground truth. So it makes sense to validate reward models using accuracy. But is it true that more accurate reward models are necessarily better teachers for RLHF?
By the way, so it's 95% of which kind of data? It's labeled by humans, or is it clear because when the LLM gives you two options, it's not clear which one you will click. So is it clear which is the best answer in this data set?
So it depends. So in some data sets, it's a bit more ambiguous if it's general preferences, right? Then maybe different people will have different preferences.
So how can you get 95% then?
So in some of these data sets, it's more concrete, like if you have a math problem or you know exactly which type of solution you're looking for. So it's true that if you look like a human, how humans agree, often it's around the 70, 80%, but these data sets contain a mix and some of them are heavily skewed maybe to more where you know if this result is correct or not, then it's higher.
Always turn this the Boolean value into 1 or 0 binary.
Yeah, so accuracy, yeah, it's just 1 or 0. If you rank them correctly, you have some.
It seems like you may be missing a lot of information. This can be a very bad inequality or a mild mistake.
Yeah, and that's a good point because this is actually what's going to be a lot of what's behind the theory that I'm going to prove. So very good point. You're going to see how this plays out exactly. The ranking accuracy gives you not enough information. It's going to be my next point. Okay, basically, okay, the question up here.
I would like to answer this question.
Yeah, okay.
Naive answer to this question, right? I mean, obviously not, right? Because you can put just ones for all the good responses, zeros for 0-1 loss. It's horrible, but it's a horrible loss function or a horrible reward model.
Yeah, but why is it a horrible reward model?
You don't know how to optimize the 0-1 loss functions, right?
So
It's horrible for our algorithms.
So it depends. It's a bit more complex. So in some cases, 0-1 rewards can be perfectly fine.
They are fully accurate, right? I mean,
Yeah, and in some cases, it can also be great. But there's okay, when will they not be good? This is what we're actually going to check.
But usually people don't do this. They take the log loss, and it's critical to state exactly what you're assuming the transfer function is. The transfer function, the one that takes the two rewards and decides how the human reacts, is the one where we are maximizing, and it's a critical component in the maximization, and therefore you should judge it with respect to it. And usually, people do log loss if they want to really do something serious.
So correct me if I misunderstood, but this is for training the reward model. So the reward model, you're training it with a log loss with respect to maximize the likelihood of the preferences. Here, we're not talking about that. You have some reward model, somebody gives it to you. Let's say you have a list of 10 reward models. You're using this reward to train using policy gradient methods, your language. Okay, which reward model works better? So put aside how we train the reward model. We're not going to discuss this. We assume that somebody gives us
it will work better with our current
algorithm.
Yeah. Really based,
using policy gradient methods, right? So maybe it's not surprising to some of you, but at least in contrast to how reward models are currently evaluated, some conventional wisdom, more accurate reward models are not necessarily better. And we're going to show this by taking an optimization perspective. Okay, we're going to consider when does the reward model allow for efficient policy gradient optimization. Okay, when you train using it, will the reward increase at a satisfactory rate? Where the reward that we really care about here is the ground truth reward. We're going to consider how proxy reward evolve and also the ground. And the first thing that we're going to see is actually, regardless of how accurate the reward model is, even if it is perfect, it can still lead to very flat objective landscapes that leads to optimization. And this is the intuition that I think some people here already have. We're going to formalize exactly which measure captures this optimization. I think this is going to be especially the useful one that we can then verify in practice. And this is a theoretical result, which based on, we're going to prove and show empirically in standard settings that more accurate reward models are indeed not necessarily better teachers. And we're also going to discuss other limitations of existing benchmarks. So in the next part of the talk, I'm going to elaborate on each of these. Okay, so first, I would like to introduce a key quantity. It's a very simple one. It's the variance of the reward variance. Pretty much what it sounds like. Okay, this is the variance of the reward that the reward model gives us with respect to our policy, pi theta, and the prompt fix. Importantly, the randomness here comes only from the outputs sampled from the language model, from the policy pi theta. Okay, so it's the variance of the reward with respect to these outputs. To estimate this quantity, you just sample multiple outputs, compute the reward, and estimate the variance. As simple as that. Here's the exact definition. Okay, nothing special here. It's the standard definition of variance, just to be clear that there's nothing hiding behind this definition. The way that you can interpret this, okay, from the perspective of the reward model, is that it measures how it separates the rewards that it gives to outputs that are probable under our policy. If it gives roughly the same reward to all outputs that our policy is likely to produce, then the variance is low. But if it separates them, it will not be. So another name you can give is perhaps some form of margin, okay, the margin for the reward. And note that this is in contrast to accuracy, right? As was brought up before, accuracy only depends on how the reward model ranks different outputs. It disregards completely the degree of separation. And because of this, reward variance and accuracy are effectively independent properties of the reward. And what we identified that reward variance is intimately connected with optimization. Specifically, when it is low, it will take us a long time to increase reward. Okay. The time that it takes, so the expected both proxy reward that we train with, and also the ground truth reward, to increase by any desired amount. Okay. This time grows inversely with the initial reward variance. What you have here is an average over the trained set of prompts, and the variance of the reward with respect to the initial pulse, and some inverse relation. The exact power is not super important, but what's important is that this implies that when the initial reward variance is low, it will take you a long time to reward.
That's independent of how you set the regularization.
And
you add the regularization to it.
yes. So this, regardless of the regular. So essentially, this issue arises by maximizing this. I'm going to show you in a bit. Maximizing this, and you show that the regularization doesn't help you escape the flat area, so it doesn't matter. Yeah. But even if you don't have this, doesn't stem from the regularization, but the regularization doesn't.
What algorithm applies to it? Not to any algorithm.
Policy gradient. So we're taking gradient steps to maximize this plus some regularization, but or only this. So the theorem itself, it holds for gradient flow. You can also have a version for gradient ascent with a fixed learning rate.
Yeah, presumably, if you, for example, normalize gradient or something like that, could help a lot, right?
So there are methods over normalizing that can help, but the ones that provably help are impractical. There's not natural policy gradient, because there are many people in the room that probably know this method. The RL literature, actually, it solves this issue. But the thing is that this method is impractical. It's a preconditioning method that requires computing a matrix as the size of the parameters of the model over the parameters of the model, and then inverting it. So this problem is actually solved in theory, but not in practice.
Just plain normalization, L2 normalization.
So not exactly. There are some complexities to it in the sense that, like, for example, if you do L2 normalization, then it depends on how good you estimate the exact gradient. Okay, here, what is the problem? And to give us more detail, the expected gradient of the objective, it turns out that it vanishes whenever the variance is low. Okay, this means that in practice, you often estimate this gradient. So this estimate may be very noisy, not exactly zero. And if you do these normalizations and you're not careful, this can actually cause instability. So it's a bit tricky, but there are papers that following our works that try to do different normalizations to improve this.
Just what was first the time, it's like a critical, especially time. It's not discrete time, it's like time.
Yeah, but you can prove the same result for gradient descent with a fixed learning.
And it's like for the time to increase by epsilon or something like that.
So for any, let's say you want to increase the reward by an additive constant of gamma. You can also frame this, I want to be 1 minus epsilon, like epsilon close to the optimal point, but this is a bit stronger because it's not even, you coming epsilon close. Even if you just want to improve by epsilon, in any case, you have to pay something that
From
looks like
initialization
this.
to something larger from what I have.
By an
right
additive
now,
constant.
by an additive constant.
Any additive, yeah. So this term is multiplied by this something that depends on this additive constant, but you anyway have to pay something that depends on the variance.
But what if you multiply like all the reward by 100?
Yeah. So this is essentially equivalent to multiplying the learning rate. So in some sense, yeah, you can escape this lower bound, but you're not really going to get faster convergence. And there's no free lunch. Right? If you just increase the learning rate arbitrarily, then you'll just get instability.
So you normalize it somehow that the
Yeah.
variance, unconditioned variance is
So here the way normalization comes into play is the fact that the rewards are normalized. So one case in which reward variance is low, which is maybe less interesting, is where all rewards are near zero. And then you can just normalize the rewards, multiply by a scalar, and that's it. But for a given scale, let's say your rewards are scaled to be between -1 and 1. This also according with practice. People typically normalize their reward model. Then reward variance measures how well you separate the outputs. And for this normalized reward, then yeah, you have this issue. The question, okay, how can you improve optimization? So you can escape the lower bound by just scale it, but not in an interesting way.
What about nonlinear transformation of the logic? If I remember correctly, it's a problem that existed already back when, let's say, with GANs, right? If the discriminator is too strong, there's not no training signal for the generator. But then people fixed it with taking the log of P and things like this.
Yeah, so you can think of doing all sorts of different transformations to increase the variance, and it's a good question. I'm going to touch upon like people have done these sort of things, but I'll say that it's still not clear what's the best thing to do. Also notice that this is a necessary condition. Okay, low reward variance is bad. I am by no means saying that maximum reward variance is the best thing to do. Okay, so this is a necessary condition for a good review. So it's still not exactly clear, and I'll talk about it at the end of it. What makes the best review? Okay.
One thing that's just to make sure I understand, this is a variance conditioned on X, right?
Yes. So it holds.
Quantity, you're fixing X in a sense. Right?
So it's an average over the training set. So this is the property of the training, right? So this is an average over the training set. For every prompt that the variance is low, the gradient vanishes, and this bound just depends on your whole training set.
It matters is the average over this sample.
Yeah, like actually more generally, also empirically, if you have a prompt that has low reward variance, then overall you're not going to learn much. But if you just want to bound overall average progress, you can do it with the average. Okay, so getting back to our main point here is that, okay, before that I'll say that I'm giving this in the context of language models, but this result holds much more generally. It applies to any reinforcement learning setting where you have a policy that produces a distribution of our outputs using the softmax. And this is a very general condition, pretty much applies to any practical reinforcement learning setting where you have a finite set of outputs, because this is the standard way to characterize policies. And for our purposes, what it implies is that we need the reward variance to induce sufficient variance if you want to have sufficient optimization. You can think of this as a necessary condition for a good reward. And as you might have noticed, okay, accuracy doesn't appear in this slide. This doesn't depend at all on how accurate the reward model is. And because of that, we can use this to prove that more accurate reward models are not necessarily better. If for any initial policy that you give me, you can have even a perfectly accurate reward model, and on the other hand, a relatively inaccurate one. It still needs to get some pairs of outputs correctly, but can get most of them wrong. And if you train with the perfectly accurate reward model, then the ground truth reward will actually increase arbitrarily slower compared to the inaccurate one. Okay, we can make the gap between them arbitrarily large. And I'm giving this extreme case of a perfectly accurate versus inaccurate one, but more broadly, we prove that optimization speed can be effectively independent of accuracy. Okay, for any accuracy value that you can give me, there is a reward model that works great, but another that works poorly because it induces flat answer. To get a better sense of where this result comes from, I believe it's best to look at an illustration. It's the proof by picture. So, on the left, what you see is the ground truth reward that we want to maximum. The directions are directions in parameter space. We start from the gray dot here. This is the initial policy. To maximize the ground truth reward, we need to go to the top left. For our reward model, accuracy and reward variance capture different aspects. accuracy roughly translates to how well the reward model agrees with the ground truth reward on which directions are good. If it is very accurate, it will also tell us, let's go to the top left. This is great. If it is inaccurate, it may tell us to go to some other directions, which is actually bad under the ground truth reward. Okay, so we do want our reward model to be accurate. But even if it is perfectly accurate, what we prove is that when the reward variance is low, you get a very flat objective landscape that leads to slow optimization. So you can have a perfectly accurate reward model, but if it induces low reward variance, you're pretty much stuck. And you can have a less accurate model that still needs to identify some good directions. And if it induces high reward variance, you can get faster increase in ground truth.
But again, so
Yes.
no very clear. But if it's fully accurate, then it's always good. Or even if it's fully accurate, it might be not the best reward model for learning.
Yeah, so even if it's fully accurate, it still may not be the best. Yeah. So in a sense, these are two independent aspects. So we want both of them to not be low.
How is it different from what we know in classical supervisor? 0-1 loss is fully accurate. And again, it's a horrible loss, right? Usually it's surrogates. That's because of this how is it different from
So if,
in the classical supervised learning sense?
so know that a reward that gives you 0 and 1 rewards may not necessarily have low reward variance. So reward variance, it depends also on the initial language. So actually, if you have 0, 1 rewards, but the reward model identifies from the outputs that the model produces which ones were good or not, then it's actually a very
For the
good
training
training.
set, it can be fully accurate. You can do one reward, right? 0-1 rewards.
Yeah. Yeah, here I mean, even if it's perfect
And it's
over
horrible.
all the outputs, even not your training set, any outputs that you see, it can still be good. So the fact that if it gives you 0, 1 rewards inherently doesn't mean that it's bad. Kind of reward variance captures when it will be bad. So if you get only 0, 1 rewards, but you only see zeros or only see ones, it's bad. But if your policy gets zeros and ones, then actually it can be great. So there's nothing inherent in giving a 0, 1 rewards.
Completely flat everywhere, just like a step function, right? And then
So-
we will not be able to optimize.
So this is the interesting part. Even if the reward is like a step function, it doesn't mean that the objective landscape for your policy is a step function, because you're essentially what you're maximizing, right? You're not maximizing through reward, you're maximizing through this. So you're essentially having this is just a coefficient, right? You have a linear combination of these probabilities. So even if the reward is 0, 1, your objective landscape is not step function, right? So it's a bit different technically. So how reward variance is what exactly captures this, in the sense that if you have 0, 1, but your policy is only focused on zeros or ones, you're for that support. But if it has some zeros and some ones, and actually the objective is quite good. So it's like it's intuition. The intuition is somewhat correct, but it's not always. So it's not necessarily because it's either zeros or ones. Okay.
Can I ask a question?
Yeah.
And the result is for, like, so the setting is it like exact optimization setting or stochastic optimization?
Yeah. So we assume access to exact gradients in the analysis. You should probably be able to generalize this also to the stochastic setting where you estimate the gradient. But yeah, it like adds a lot of complexity. Yeah. In practice, the experiments that we run are obviously when you estimate the gradient.
So the reason that I'm asking is that like a lot of practical work, I think that they also kind of showed something of the sort, kind of want to have like both positive and negative examples in your batch.
Yeah.
So that's even like more like a batch set rather than stochastic set. So
Yeah, so this case shows that even if you have like perfect knowledge of the whole distribution, you can refute everything, and you still have a problem. Even if it's not just a batch problem, it can be a whole population. It gives you low reward variance, and you're still, it won't help you if you can see all the possible outcomes. Right, so this was the main essence behind the result that I just showed. And in practice, you can also see this in standard settings. Here, this is just a small subset of the experience that we have. This is a 3 billion parameter language model. The data contains concept, just general questions that people can ask ChatGPT. And we're going to look at how the ground truth reward evolves as a function of the epoch of the training for 2 reward models. One which is moderately accurate, and the other in red, which is actually perfectly accurate, but induces low reward variance. And the main point here is that in line with our theory, okay, despite being perfectly accurate, the red reward model substantially underperforms the less accurate reward model. It leads to slower increasing growth. Another observation that's worth making here is that the same reward model can work well and induce high variance for one language model, but poorly and induce low variance for another. And this is because reward variance also depends on the policy, on the language. You can formalize this in a similar manner to what I already showed and prove that for different language models, different reward models can work better in the sense of leading to faster increase in parameter reward. In practice, if you just take 3 different language models, it is the groups in the plot, and use different reward models, each color here is a different one. And you can see also that, okay, for this, the blue reward model works better, so the purple. For different language models, usually you see that different reward models are best. The reason I believe this is interesting is because this implies that when we consider what makes a good reward model, we need to take into account the language model being aligned. Okay, there may not be this universal sense in which this reward model is better than that one, and existing benchmarks, which exactly measure how well the reward model works independently of your language model, they are fundamentally limited because of this. They do give us some information, but they can't really tell usually which reward model will work better for your language. Okay.
Can you give some intuition for this?
Yeah. So, for example, let's say you have 2 language models and they produce distributions over different sets of outputs. You have a very large set of outputs in language, and you can have one reward model that gives high variance and identifies well which outputs are good or not for one language model, but for the other, it gives them roughly the same reward. It doesn't really distinguish between. So it will work well for this language model, but not for that one. And you can have another reward model, which is exactly the opposite. And if you just evaluate accuracy on some fixed data set, independent of your language model, then it won't necessarily tell you if it's going to be good over your language model, the outputs that it will produce. Yeah.
Should we say that the variance that we talked about is kind of a surrogate for the normal gradient in some sense, and therefore it's slow than the gradient.
So it's not just the gradient, yeah, it upper bounds the normal of the gradient, but also the higher order derivative, the Hessian. So it essentially gives you a measure of how flat. When it's low, you're in a very flat.
If it's sufficient that the gradient is small, then we are.
The gradient, you need also higher order derivatives to be smaller. If the gradient is small, then maybe it can increase fast, so you are not really stuck. But the gradient, also the higher order derivatives.
All of these are bounded somehow.
By the variance, yeah. This is kind of the new connection that we made with reward variance and policy gradient optimization more broadly. Is that reward variance actually bounds the norm of the gradient and other cases.
So what you basically said is that some language models already resolve this, and they don't produce outputs that are offensive in some sense, but they might produce outputs that are offensive in another sense, and you need a reward model to fix what the underlying model doesn't do on its own. I mean, I don't, because you said the output in areas in which the reward model doesn't rank or doesn't do anything, and it doesn't matter for performance, it means that the underlying language model probably is already okay.
So this is one case where reward variance can be low, and this is perfectly fine. Like if the language model is already great, then reward variance is low because you're in your document. But in many cases, it's not. The reward variance can be low even if you're bad. This is the cases which are problematic. So it's true. Like reward variance is low is only bad if you're not already good, like the language model. Okay, so just to quickly summarize what we saw until now, we talked about what makes a good reward model for our chef, and we took an optimization perspective on this question. We saw that beyond being accurate, we needed to induce sufficient variance, but not sufficient optimization, and we used this observation to also prove and show clearly that more accurate reward models are not still better, in contrast to how they're currently being evaluated, and we also mentioned other limitations of existing benchmarks. And the overall takeaway from these results is that we need to take into account other properties beyond accuracy when we design reward model evaluation protocols. And reward variance is another important quantity that we identified, but there may be others as well that we're not aware of. And what I would like to do now is just spend a few more minutes on reward variance, because I believe that is a useful measure. Okay, it depends on 3 aspects, on 3 factors. First is the reward model. This is what we mostly talked about until now. It also depends on the data, on the prompt X. and on the policy typing, the language. And through these different dependencies, it can shed light on other aspects of this alignment process and also has practical application. When we focus on the language model, then an empirical finding that we make is we see that if you do an initial supervised fine-tuning phase, this amounts to you collect a set of labeled examples, prompts, and outputs that you consider to be at least moderately okay, and you just train the language model directly to produce these outputs for a short while. This can substantially increase the reward rates initially. In other words, through our theory, you can think of this as it helps you find a less flat initialization for RLHN or the policy benefits. And this sheds light on why doing this initial supervised fine-tuning phase is often helpful in practice. It's somewhat of common practice these days, and can also give guidelines to when it should be necessary. When we move to the data perspective, then follow-up works have proposed data selection algorithms based on theory. The idea is that you can train on prompts that enjoy a high reward variance because you're going to more effectively learn over them. And you can have these curricula that order the data points according to their reward variance. And if you go back to the perspective of the reward model, then fall papers have also proposed new reward transformations and changes to the policy grade update rules in attempt to improve optimization based on our. For example, you can transform the rewards to try and improve variance while maintaining how accurate it is. This all goes to show that, at least in my opinion, reward variance is a key quantity for successful RLHN. And also reinforcement learning more broadly, at least policy grade. Okay, at minimum, it can help us identify optimization issues, which prompts we're not going to learn much over. But beyond that, you can also use this to develop new algorithms. And I believe that we're just scratching the surface in terms of what we can do with the relation between reward variance and optimization. Just one final remark on RLHF before we move on. Is our question? Yeah.
So, just a quick question. So, how does that compare to the norm of the gradient? What's your take on that? And like, is there any reason for the variance? And let's say like, so another quantity that maybe also intuitive is, you fix a prompt and then you calculate the norm of the gradient once that's at
Yeah. So you're saying in practice, what is the usefulness of using reward variance over just a normal gradient? So I think perhaps there's two use cases. The first one is efficiency. It's a lot more efficient to estimate the reward variance as opposed to the gradient norm because you don't need to do the backward pass. And the forward pass is much more efficient. And the second, which I think requires some motivation, but it's a very interesting direction that I still haven't done, but I think it was that I believe there are advantages in terms of how efficiently, in terms of samples, you can estimate the reward variance compared to the norm of the gradient, right? The reward variance, you have very classical bounds. It's a very easy estimate to do. Like you only kind of logarithmic, like if you want like the high probability to get an accurate estimation, you only have 1 over epsilon squared and logarithmic in the probability of making an error. It's a very easy quantity to estimate. And the gradient in some sense depends on all the parameters of the model. And I'm not sure like how efficiently you can guarantee that you're estimating. So I haven't formalized this yet, but I feel that this also might be a difference. But the first one piece is also makes efficient, more efficient.
There's a non-trivial insight you can gain for reinforcement learning with a viable reward against learning or reward model. So
yeah, so that's a great question. So here we talked about reward models. Another setting that reinforcement learning comes into play in language models is where you have a reward function. Let's say the model solves a math problem, and then you give it a reward of 1 if it's correct and 0 otherwise. The theory applies also to this. There is the question, okay, if you have low reward variance, should you change the reward because then you're risking reward hacking? So it's not clear, but it can give you, for example, insight.
how do you augment variance per language model without changing the actual ground truth statement?
Right, so you can try to change the reward and modify it, but even if you don't want, then another thing that can be useful, for example, is these data selection algorithms. They're actually, most of them are done in this setting. And you can look at which prompts you're not going to learn much over and try to filter by that. Also, if you see that your variance is low, you can just perhaps do more supervised fine tuning. So even if you don't want to touch the reward, there are other things you can do to affect reward. So just one final remark about RLHF. Until now, we discussed how the properties of the reward model, okay, the accuracy and the variance, how they affect RLHF. And these properties, they depend on the type of the reward model we use. There are several different types that you can choose from today, yet we don't really understand the relative advantages and disadvantages of the different types. And this is something that we just began to address in this paper. I'm not going to go into the details of this work, but what I did want to highlight is that there's still much more work to be done. We still don't understand nearly well enough this full pipeline, how the reward model type affects the properties of the reward model, and then how they trickle down to the language model. Okay, so that wraps up what I had to say about the reinforcement learning approach to alignment. And now I'll just briefly discuss the direct preference learning approach and conclude future directions. So the motivation behind these methods is that while RLHF can work great, it is also quite expensive. Okay, it's this two-step approach where you first train a very large reward model, then you try to align it, and then you align your language model based on it. And the question is whether we can just do a one-step process, directly align our language model based on the preference data. And indeed, there have been several different methods that propose exactly this. The idea is very clean and simple. You just take your preference data and directly plug it into some loss function that depends on the gap between the log probability. To minimize this loss, we need to increase the gap between the log probability. Intuitively, what we might expect is that when you minimize this loss, the probability of y plus, the preferred output in your training set, it should increase, and that of y minus, this preferred output in the training set should decrease. But if you run these algorithms in practice, what you often see is that both probabilities tend to. Okay, so here's an illustration of what you often get. The log probability of the function of the training set, that both tend to decrease, but the gap still opens up. This means that the loss is stably minimized, but the way that grain-based methods over existing models tend to reduce the loss is by sending both towards zero, just at different rates. What this implies is that there exists some other outputs. Here it's C in this illustration that must increase in probability, and they're not in our training set. We're not accounting for what they are. And this is what we call this phenomenon likelihood displacement. So this may not be problematic if this Z is similar in meaning to y plus, to what we intended. Consider this is benign. But maybe this can be catastrophic. What if the Z is completely opposite to what we intended? And despite the fact that people observed empirically that y plus can decrease in probability, it was not clear why this happens and what are the implications of this. Can it be catastrophic? In which settings? And what can we do about it?
Is it even clear that Z is getting smaller than y plus?
Oh, no. So this is just an illustration. There is an output that must increase in probability. It's not necessarily that it will be more than y plus, but in many cases, I don't see it does lead to these types.
So can the divergence term accounts for that? Because it's basically the probability of the output, right?
So in this type of method, usually there is no KL divergence. You're just minimizing this output.
No, the TPO is
Implicitly, but in practice, it doesn't really matter. This is kind of why this, implicitly, it is derived from the scale. And in the asymptotic sense that if you perfectly optimize the objective, you get the same result. But over a fine training set, you actually get different things. And this is part of the reason why this phenomenon happens.
L is some kind of softmax.
So L, for different variants, you have different L's. For one popular choice of L is kind of minus log sigma, kind of a binary cross entropy.
Then the field shows up.
And then you can, this is equivalent to doing RLHF in the sense that if you would have optimized over all the data in the world for infinite time, you get the exact same solution. But over finite training time, that's kind of, and just to skip to the main point here, I'll say that we do show in our work, okay, not going to go into the details here, I'd rather spend time on the future work, and that this can lead to weird behavior where the alignment completely fails. You try to align them all to do one thing, and actually completely unalign the model. We also have doing experience that explain this and give a measure that helps you mitigate the problems by filtering better data. And now I'd like to focus on the future work and the time that I have left. So just to quickly recap, I start by outlining three aspects that I view as fundamental ingredients of general purpose models: rule knowledge, alignment, and inference. And we focus on alignment, where for the reinforcement learning approach, which we mainly discussed, we saw that it can suffer from slow optimization when the reward variance is low, regardless of how accurate the reward was. We use this to show that more accurate reward models are not necessarily better, and discuss limitations of existing benchmarks. And also we saw that this has practical applications for data selection algorithms, policy gradient methods, and as I said, I believe there's still much more to be done. Then I just briefly skimmed through the direct preference learning approach, which the main point here is that it can fail in these weird ways if you're not careful, and that through our theory and experience, we can identify a quantitative measure that allows you to find examples that cause these failures. And this also has practical applications in terms of data filtering and how maybe you can modify these algorithms to mitigate these issues. Going forward, in this talk, I focused on the current dominant approach for alignment, which is reward-based. And the recurring theme is that the limited understanding here can lead to undesirable outcomes. Whether it's inefficient training or safety concerns, these issues are just becoming more costly as the scale of current models increases. And because of this, I believe that it's going to be important in the coming years to further develop our understanding and give guidelines for reward-based alignment. We want to ensure that this is done efficiently and reliably. And aside from the research that I presented today, I would like to highlight 3 avenues which I believe are particularly promising towards this goal, and at which I already began making initial steps. So the first one is what makes the best reward, or the optimal reward in some sense. We saw necessary conditions. If a reward model has low accuracy, if it has low variance, it's probably bad, but there's still part of the picture missing. What makes the best reward? If I give you a list of 10 reward models, nobody knows today to select which one will work better, aside from just running all, which is expensive. And we're now doing a more fine-grained analysis of policy gradient optimization with the hopes of shedding light more about this aspect. The second relates to the problematic objective landscape of policy methods as well. Can we use that to discuss what makes a good reward model, but can we just directly address this problem? Can we change the optimizer or the parameterization and solve this issue? Yeah, this is also something we're considering. And also, there is now a big challenge with making sure that the model remains aligned in production. Okay. Typically, we train, align the model, and deploy it as a fixed artifact. But there's growing use cases for adapting it online. This creates a challenge in ensuring that it remains aligned, doesn't lose capability that it previously had. So in a recent work, empirically, we find that training a model using reinforcement learning, where outputs that it itself produced can be robust to becoming misaligned. And we still don't fully understand this, but I believe that if we will, this can open up avenues for this direction. Now, if we look further into the future, though, okay, this is all about reward-based alignment, it's going to be important to go beyond, I believe. Okay, a very major limitation here is that this relies on limited feedback, get a single scalar per output. Ideally, we would like to leverage more rich, structured forms of feedback that convey more information per unit of effort. If someone is going over your output to tell you it's good or not, maybe it's not that much more effort to also tell you why. And to be concrete here, we put side by side reward-based alignment, potential future alignment paradigm. Then for reward-based alignment, okay, we want to maximize some results. And we get a preference label or some proxy reward. We have fundamental building blocks to use, policy gradient method, policy-based methods, value-based methods. I'm being very coarse-grained here, but the idea is that although our understanding of reward-based alignment is limited, at least the framework is clear. When we move on to potential future paradigms, okay, first it's debatable how we found the right definition of what makes an aligned model. But let's say we do have some predefined metrics, some ground truth reward that we want to max. Now we would like to leverage more structured, rich types of feedback, natural language comments, rules that the model needs to obey. But now when we have this type of feedback, we no longer have algorithmic building blocks to use. And this is a challenge both for practitioners and for theorists. How can we develop algorithms that learn from this type of feedback? And how can we formalize their advantages compared to reward-based? Where one main potential advantage is it can circumvent the issues that I showed today. Maybe they can enjoy better optimization and sample complexity, and also avoid these unintentional unalignment phenomena, which I just briefly mentioned. At a high level, they stem from the fact that the signal of learning from these rewards can be ambiguous. And this type of feedback can be more comprehensive. And lastly, alignment is just one part of the process. Okay. As we make advances in understanding alignment, this will need to go hand in hand with better understanding other aspects of general purpose knowledge, inference, and rule knowledge, among others. how we do alignment, this will heavily affect inference and vice versa, and they both depend on the knowledge that the base model has. I believe it is difficult to understate the importance of developing a fundamental understanding of these general purpose models, given how ingrained they are becoming in our everyday life. And I hope that through a combination of theory and real world experimentation, can get there. That's what I had to say for today. Just like to thank my collaborators at Tel Aviv, especially my buddy Nadav, and at Apple at Princeton, where I'm hosted by Sanjeev Arora.